Before that, can you hear my voice?
Yes.
Okay, so let us continue back the fractional factorial design. Okay, so the fractional factorial design, as I mentioned, we only run the fraction of the complete full factorial designs. We only run fraction of them. So therefore, if you have the 6 factor here, altogether is 64 runs. You maybe only run for the half of the one half of them is 32 of the runs. 32 of the runs it means that 32 treatment combination, or you run just quarter of them. Okay, so you only run 16 runs and so on. So in the chapter here, we are studying what is called the two-level fractional factorial design. Okay, so I have give you some explanation about what is meaning by the generators, what is meaning by what is the names, the terms called the generator, and then you have a 1/2 fractional 2 power k design where they given the notation as a 2 power k minus 1. Okay, and then you need to use what is called the generator. Okay, so how we want to form it out for the fraction of here. In this case, we are studying is a 1/2 fraction of the 2 power k design. So means that in the following example, we have a 2 power of 3 altogether is a 8 treatment combination. So we only run 4 of them. Okay, 4 treatment combination. So you have altogether 8 of them. You only run 4 of them only. So which one you should be run? So we need to group them according to what you set the generator. Okay, the generator over this example we set is a ABC here. Okay, so we set the generator as a ABC so that we arrange the treatment combination according to the plus sign and the minus sign here. So therefore, you either run for the first part of your treatment combination or the second part of your treatment combination. Okay, so you need the generator. Okay, so this generator will be related to the later on what we call as a restoration. Okay, so this is what I show it to you. You can run for the positive side, and then you also can run for the negative side. Okay, so they combine together become the full factorial design, but you only run for the portion, just a portion of them, either positive side or the negative side. Okay. So we have a following one is what is called by the defining relation. Okay. So in the defining relation here, we are looking at the okay, is a I is equal to ABC. As you can see, the I here is always positive. I here, we give here the notation here is all the positive here. Okay. So the defining relationship here will help you to lead you to the another thing is called the aliases. Okay, so before I go through the aliases, I have given you the notation here. If you want to find the contrast of them, so the A of them is a LA, or you put the bracket of the A here, is stand for the A minus B minus C plus the ABC divided by 2. Okay, so how we want to get it out? You from here, you just use the first half of them to consider the plus sign, plus minus sign, and the B is plus minus sign, and so on. So if you observe the plus minus sign here, you can observe that A and the BC, their sign will be the same. Therefore, their contrast will be the same. Similarly, you observe the B here. B is a minus plus minus plus. You also have a minus plus minus plus. So B and the AC will be the similar, the contrast. And then the C and the AB, they have a similar contrast of them. So this one will apply for the negative side here. You can be measure it out. Those of them have a same sign, okay? Where they have a, because of the negative here, they have multiplied by negative. Then the multiply by negative, you have become the two positive, 2 negative. This one will be same like the A part A here, okay? So here I have shown to you that if I write the following one, the effect here is a contrast over 2 here. This one was similar to the BC, B was similar to the AC, and so on. So in that case, we will written as the following one. In fact, you are estimating the effect of the A is actually is same like the L for the BC. Therefore, if you're estimating of the effect of the A, actually you are estimating the effect of A and the BC together. Okay, so means that you have a two information together. When you run the you calculate the effects, you calculate is the effect from the A and the BC. Similarly, for the B also is the B and the AC. Okay, and the C will be C and the AB. So this one is what we call as aliases. So therefore, we say that the A and the BC are aliases, the B and the AC are aliases, and the C and the AB are aliases. So we give the notation as A plus a BC, B plus a AC, and the C plus AB. So here I also told you that, in fact, when we estimate the ABC, we are really estimating the A plus a BC. Okay, we are estimating these both together. Okay, we are not purely estimating the A because we only run the one half of the designs. We don't run the full complete designs. If we run complete design, then of course you can obtain the effect A, B, C, and so on. But now we expect that we only run one half. We want to base on the one half to obtain the information whether which are the important factors. Okay. So I have introduced for you the name of here, alias. Okay. Then after that, I will introduce also with you the defining relation here. Okay. So to find the alias structure, what you can be start from the defining relation I equal to ABC. You just multiply by A equal to BC, B equal to AC, and so on. Then you can get all the alias structure come out. So use A is equal to BC, B equal to AC, and the C equal to AB. Okay, so these are the things is what you can get from the alias structure. Okay, so I showed you only for the one half of the fraction. You still have another half. That one is called the alternate or complementary fraction, where with the negative here. So basically, you can run for the positive side or you want to run for the negative side. Okay. So the complementary fraction also the similar thing. Okay. So after I introduce for you the defining relation, I choose the I equal to ABC as a starting as their generator, and then I equal to ABC is a defining relation, or I equal to negative ABC as a defining relation. So this thing we select for the ABC, this thing was related to the restoration you have. Okay, we want the restoration is as high as possible so that the alias structures for the main effect, two-factor iteration, and the three-factor iteration, they have a different relationship of them. Okay, so this one is a restoration tree. In this example, restoration tree, why they call tree? Because the main effect is alias with the two-factor iteration. As you can observe here, A and the BC were together. You are estimating the A, LA prime. Actually, you are estimating the A minus by BC. So you are estimating both of them. Therefore, the A and the BC will have a alias structure. So if this one happen, this one is called restoration tree. Okay. So here also I have told you that we do the confounding, we do the alias structure also can be based on the what you have learned before is the ABC confounded with the block. We just grouping those of them at the plus and the minus sign together. Then you only run for the first block or the second block. Okay. And then I also discuss with you if you have a here alias structure for the A plus BC for the first half of them, and then you run for the second half of them. You have a A prime, A minus by BC. Then if you take the average of these two, you will go back to the factor of the A. So this one will tell you that if you run for the first half and then you run for the second half, then you get back really the effect of the A. Okay. But now our issue over here is we want to run only the first half. We do not want to run the second half. So this one is an objective for our study here. we want to run the fraction. Okay, the fraction of the design. Okay, so this one is a restoration I have mentioned to you before. If you have a restoration tree, it means that the key point is a main effect is not alias with the main effect, but the main effect is alias with the two factor iteration, and some of the two factor iteration may alias with each other. So that one is a restoration tree. You have another one restoration 4, and then the restoration 5. Okay, here are the different restoration what we have discussed before. Okay. So as I mentioned, we need the restoration is as high as possible. Okay, why we need the high restoration? Because as you can observe here, if no main effect is alias with any main effect or any two factor iteration. So this one will say that your main effect or the two factor will not alias with their main effect or two factor iteration. But the two factor iteration are alias with the three factor iteration. Okay, so if the three factor are alias with the three factor iteration, this one will say that if you have a certain factor, if you have a certain factors, for the three factor iteration, you can be assumed they are not important. For if the three factor iteration they are not important, then what you calculate out will be calculating the two factor iteration effect itself. Okay, because they have a linear structure with this thing. So this one will means that the A, let's say for example the BC, okay, plus the three factor, it will be plus the A, let's say the AB, ADE. Let's say we have this thing. If we want to estimating the BC, okay, if we want to estimating the BC, actually you are calculating the BC and the ADE, for example. But if the two factor are alias with the three factor, this one is what they look like. Then if we can assume that the three factor iteration is not significant, so this one will go into the 0. Okay, if they equal to 0, therefore when you calculate the effect here, you are estimating the factor BC alone. So this one is why we need the height restoration. Okay, if for the restoration for the 3 here, you have A is A plus a BC. Main factor will the alias with the two factor. So most of the time, two factor iteration, they are significant. So if you assume the BC is not significant, of course you can estimate the A directly. But is it the BC really is not important? So this one will be in the one question mark here. Okay. But for the 3 factor, 4 factor and onward, we most of the time we will do the assumption say that they are not really very important. But until the two factor iteration, we still maintain it. Okay, so this one is mentioned about what is a restoration for each of the case. Okay. So here actually I stop. If I'm not mistaken, I will stop somewhere around here. Okay. So for the here the construction of the analysis of 1/2 here. So the 1/2 design, we choose the highest restoration may be constructed by writing down the basic design consists of the run of the full factorial 2 power of k factorial. So means that if you only want the run half, so you will choose you write out the full factorial of the 2 power of k minus 1 because you will less one of them. Okay, one of the factor you will less one of them. So you only run the write down the basic design consists of the 2 power of k minus 1 factorial design. Then adding the k factor by multiplying the plus minus sign level. Okay, and then finally you will get your factors from the ABC until the k minus 1. So this one is similar to just now I have shown it to you. You have a ABC. You do you have 3 factors A, B, and the C factors. 3 factors here, and then you want to run the 1/2. So you choose the I equal to ABC as the generator, ABC as a generator. Okay, so you will have the last one will be equal to, for example, you have a 3 factor I is equal to ABC. Okay, so if you multiply here, you get the C will equal to the AB. Okay, so this one is what they mentioned to you, that if we consist of the 3 factor A, B, C, we write it out as only the AB first, and then the third factor, the C, the K factor one, you just multiply from the defining relations here, you will get your C is equal to AB. So means that you can rewrite it down, the plus minus sign is from the ABC until the K minus 1. Okay, until the K minus 1 factor. Or another thing is what you can be view it to the fraction there, which fraction of them you can be use the idea of the confounding. Okay, means that you use the idea of confounding, you divide it into the 2 different blocks. Okay, you divided it into the 2 different blocks, then you can be define it out, the first block and the second block. Okay, so this one will be here. As I mentioned to you, I have shown you the example of here. Okay, where you use the confounding idea to define it as a block. One is a positive sign, another block is a negative sign. Okay, so this one is what they say, that if you have a general thing. Okay. So let us go through the this example, what this meaning by here. Okay, then we continue with the following one. Okay, I will stop okay, later on here. So over here, you can observe it here. This one is if you want to run to 1/2 for the 2 power of 3 design. So if you have a factor A, we have factor B, we have a factor C, we have a 3 factor here, we have a ABC here. So what they say that you run the basic design means that if you want the run 1/2, you only write for the A and the B here. So therefore, the basic design, you only write the A and the B. So you just write the plus minus sign here, minus plus minus plus. This one is called the standard order of them. Then it's 2 minus 2 plus. Okay, you run it in the following one. Then after that, your C will be equal to, you choose the highest restoration, the I will equal to the ABC. Okay, therefore, you have a C will equal to the AB. Okay, C will equal AB. Therefore, once you get this thing, you just multiply the AB, you'll get the third one, the C will come out. Okay, so therefore, you will know that under this treatment combination, under this part, what are the treatment combination you're going to run? If you want for the run for the negative side, you just have a negative value here. Okay, so here are the treatment combination you are going to run under this first part of them. Okay, so this one is what they mentioned about is under here where we have a 2 power of 3, 2 1/2 of the 2 power of 3 design. Okay, 2 power of 3 will equal to the 8. Okay, you have 8 of them, you only run 1/2 of them. So therefore, you only run the half of them. For example, here you have a similar to this idea here, 2 power of 3. You have a ABC, yeah, similar to here. If you write in the plus minus sign, then you need to write it down here. You run the ABC, the first half, or ABC. Okay, so we go to here. You can see that this two is a C is a positive, so this one is a C. This one is a A is a positive, so this one is a A. This one is a B is positive, so it's a B. So this one is ABC positive, so it's a ABC. So this one is a treatment for the if you run for the first half. Okay, you first run for first half is here. If you want to run for the second half for the negative one, so this one will be equal to 1. This one will equal to the AAC. This one is equal to the BC. This one is equal to the AB. Okay, so you have a first half and the second half. Okay, so you can be right in the following basic design. Then they will have a simple way for you to write it down all the treatment combination. Okay, so for the here, in fact, if you run for the all of them, if you run the projection of this thing into the 3-2 power of 2 design, so they will show you the diagram. In fact, in the analysis, you will run all the 8 treatment combination one. Okay, suppose you run only for the 8 of them. Okay, suppose you run the 8 of them. This one is called the full factorial design. But now we are run the fraction of them. So therefore, we only run 4 of them. So they highlight the 4 of them is here. 1, 2, 3, and the 4. They run 4 of them. Okay, so these 4 of them, if you project it out to the following direction, if you're along the BC, okay, you have the B and C here. You are studying the C here. You're also studying the B here. If you project it to the other direction, you also project to this part. If you projection here, you also project it. This point is here. This point also here. This point also here. This point is at here. So for any of the direction, you can project it to the 3-2 power of 2 design. Okay. So this one is just tell you that you can be projection into the 2 factors where you run all the full design. Okay, even though the fraction here, you 2 power of 3 minus 1 is actually equal to 4. Okay, it's a 4 treatment combination. You only run 4 treatment combination. So therefore, this 4 treatment combination is actually equivalent to the, if you have a 2 power of 2 design, you have all the 4 treatment combination for under this direction or under this direction or under another direction. So this one is just show you the diagram of the projection only. Okay. So here is say that about the restoration. The maximum possible restoration of a 1/2 of the 2 power k design is R is equal to the k. Okay, the restoration is given by the notation. The R will be equal to k. Okay, for every 2 power of k design will project into the full factorial in any k minus 1 of the original k factor. So this one will tell you that if you have a restoration, is the maximum possible restoration you have is equal to k, the first thing. The second thing is if you run similar to just now I mentioned, you can be project it to the 2 power of 2. For example here, 2 power of 3 minus 1, you can project it to the 2 power of 2. So if for every of the 2 power of k minus 1 design will project into the full factorial in any of the k minus 1 original factors. Okay, so the example will be here. If you run only the fraction of the 2 power of 3 minus 1, you can be project it to the 3 different design of the 2 power of 2. Okay, so this one is just explain to you. You can be do the projection only. Okay. The following one is this one. Of course, I don't want to read it out. I think you have a books here. So this is just an example. If detail you can be read out. I just do the summary for you all. Okay, before we go through here, first thing is this one is for the 4 factor design. The A, B, C, D. They consist of the 4 factor design here. Okay, so they only want to run for the -1, means that is they want to run only for the 2 power of 4 minus 1 design, 4 minus 1 here. So if you have a 2 power of 4 is 16 treatment combination is -1, so you have a 2 power of 3, you only run 8 runs of them. So how I want to label all the 8 runs? You don't need to list down all the 16 treatment combination of the plus minus sign. What you need to do is first thing, you write down the basic design. You list down the ABC. Okay, so you have a minus plus minus sign for all the 8 times. Then the B is a 2 negative, 2 positive, 2 negative, 2 positive. For the C1 is 4 negative, 4 positive. Then after that, we have I is equal to ABCD. Okay, we choose the highest restoration. If you have a power of 4, then we choose I equal to ABCD. Okay, because we choose the highest restoration, you have a liar structure will be less. Okay, I mean the main effect and the two-factor iteration and the three-factor iteration. Okay, the liar structure will be less. So therefore, we will prefer to choose the highest restoration. But just now I have mentioned it here. The highest restoration will be equal to the k factor here. So if the two power of the k, the restoration will be r equal to k. Okay, so in this case, if you study for the 4 factor, the highest restoration is equal to the restoration 4. Of course, if you don't want to choose the restoration 4, then you can choose the restoration 3. But you choose the restoration 3, if you study on their liar structure, you can see that a lot of the constraint there means that the main factor will iterate with the 2-factor iteration. So this one will make you difficult to estimate which are the important factors. Okay, so we will choose the highest restoration. Okay, so the I is equal to ABCD. So therefore, if you want to get the sign for the D here, then we will just use I equal to I will be equal to ABCD. Then you multiply both sides by the D here, then you get the D equal to ABC. So you just multiply all this the sign here, you get the negative. You multiply all the sign here, you get the positive, and so on. So this one is the sign for the D. So once you get the sign, you already know what are the treatment combination you're going to run for the 1/2. Okay, so this one is all the negative is a treatment number 1. If only one is positive and the D is positive, therefore we have AD, and so on. So when they decide for this design, then they're going to run this type of the treatment combination. They obtain the result of the filtration rate is 45, 100, and so on. So these are the result they have. So we expect that we run for all these 1/2. We want to make the conclusion whether we can get the conclusion, say that which factor are the important factor. Okay, whether the A, B, C, D, which factor are significant. Okay, so we want to base on this result to make the conclusion about this thing. So how are we going to make the conclusion here? Okay, so this one is I just show you about this part. Okay, so the diagram is just show you that what are the treatment combination they are going to run. These are all the 8 treatment combination here in the graphical way to show you the diagram. Okay, so as a summary, I show it to you here. We consider the example in the 6.2 because this question will be similar to the example 6.2. Okay, so in the example 6.2, when you run it out, you can check back your chapter 6, example 6.2. We have run the single replicate of the 2 power 4 design. We run the full factorial design. Okay, we run the 2 power 4. And then we plot the graph here, the normal Tory plot here. We get the result. It shows that the ACD, ACAD are significant. So this one is if we run the full factorial design. Okay, this is the result what we obtain. But now we are also using the same examples. We are using the same example as the question, but now we only consider the one half of the fractional design. Okay, we only run 8 of them. We expect that Egypt will also get the similar result as given by if we run the full factorial design. So let us see whether we get it or not. Okay, so this one is I put it here because I just want to let you know that what are the previous result you have for the same example. Okay. Okay, so now we have to here. Now what happens if we only run for the half fraction of the 2 power 4 design? Okay, instead of the full factorial design. So we only run for 1/2. Then just now we have used I is equal to ABCD. Okay, so this one is I equal to ABCD will be our generator. Then this one is defining relation. So our generator consists of ABCD. So this one ABCD means that the restoration is equal to restoration 4. Okay, this one will be the restoration form. Okay, so of course, we need to write down all the defining, using the defining relation, we write down all the aliases. So if the restoration form, we recall back what we have in the restoration form. If we are in the restoration form here, it means that no main effect alias with any main effect or two-factor iteration, but the two-factor iteration are alias with each other. So you don't have such case, you will have a AB and the CD will be alias to each other. So this one is called the restoration form. Okay, so for the main effect, they don't iterate with the two-factor iteration, but they will iterate with the three-factor iteration. Okay, so we go back to the same example here. We need to write down all the structure of here. So under here, we can use the I equal to ABCD. Okay, I equal to ABCD, we get out all the factors. So for example, if the factor A will be equal to the, because you multiply A of here, you multiply A of here, you get the BCD. Okay, A will equal to multiply the A here, you multiply A here, then you know that A will alias with the BCD. Okay, then after that, you will multiply the B I here will equal to the, this one is a B, I just write it down, A, B, C, D. So when you have a B times B, you get B squared is 1. So therefore, you have a ACD. Okay, so from here, you will get your factor A will be alias with the BCD. What we can write it down is just now, before that, we have A will be equal to the A plus the B, C, D. Okay, similar to here, you also can be write down B will equal to the ACD. Okay, you can write down the B will be equal to the ACD. Okay, so you have a first one, you have a second one. Of course, you can list down the C will be equal to the ABD. Okay, then after that, you have a D. You multiply D, you get ABC. Okay, then once you complete the ABCD, then you need to write the two-factor iteration. You consider AB. You multiply AB on the left-hand side. You multiply AD, you get the CD out. Okay, then after that, you also can have a AB, then you have a AC. AC multiply here, you get the BD. Okay, after the AC, AB, AC, then you do for the AD. Okay, you do for the AD. So the AD, you multiply, you get the BC. Okay, so you try to count how many factors you have completed. You have a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. You have 14 of them. Okay, you have 14 of them. Then plus a ABCD is 15 of them. Altogether, yeah, you have completed all the thing. Okay, so here are the alias structure of here. So this one, we can write out as a B will be equal to the B plus the A, C, D. So if we calculating the effect of the here, then actually you are calculating the B plus the ACD. So similarly for the factor C, factor D, also the same. If for the you calculating the AB, actually you calculating the effect of the AB, actually you are calculating the effect of the AB plus the CD. So these are the arrival structure of here. Okay. So now if under the alias structure here, I also will show you that this thing is just now the values of the from the question itself. Okay, we can calculate the alias structure of here. Just now, if you want to calculate the effect of the A, okay, you calculate A, we just refer to the plus minus sign here. So it's a minus 45. Okay, then plus 100. Okay, then it's minus 545. Okay, and the last one is a plus 96 divided by the, okay, divided by 4 here. Okay, then you can calculate out the effect from the A. So the calculating of this thing, you will get your value is 19. Okay, the effect of the A here is 19. Actually, this one is not purely from the effect of A. Actually, this thing is come from the A plus the B, C, D. Okay, as I mentioned to you here, A equal to BCD. Therefore, when you calculate the effect of A, is actually come from the A plus the BCD. Okay, they are mixture of both of them. Okay, so this effect, 19 of them is come from the both of them total out. So you do not know from the A or from the BCD. Okay, so of course you can calculate the rest of them. Okay, so the rest of them I can show you in the following diagram here. Okay, this one is just now I have shown it to you how to calculate the first one. Then the rest of them you can calculate out. So in fact, you are getting the A means that you come from the A plus the BCD. You are calculating the B is come from the B plus the ACD. Okay, so if you are calculating the AD, it means that AD will be calculating the AD plus the BC. They come from the both of them. Okay, so this one is what you can observe from the diagram here. Okay, so if you can observe it here, if you can observe it, this diagram here, okay, if you're willing to assume, that the three factor iteration is not significant, okay, means that all these things will be not significant. Okay, you need, because you only run one half of them, then you need to satisfy certain information. So if you're willing to assume that all the three factor iteration not significant, so you can observe that the 19, the effect is a 19. The form purely for the B is a 1.5, is quite small. For the C will be 14. For the D will be 16. So from here, if you're willing to assume that the three factor iteration is not significant, we can be guessed that the factor A will be quite important. The factor C also will be quite important, and the factor D will be important because they have a high value. We will expect that the factor B will be quite small. So therefore, they are not really not important, because if the effect is equal to 0, it's not important. Okay. Then at the same time, you can be check the iteration here. This one also is very small. So these two parts, you can be assumed that they have not the important here. But these two will be quite important here. Okay, they are quite high. So these two is come from both of them. Okay, so because of the B is not important here, so we can be say that the main contributor of the AC here is actually come from the negative 18.85 is come from the AC and BD. But because the B here is the effect is quite small, so we will think that the BD also will quite small. The main contributor we will guess they come from the AC. Okay, similar to the here, if you calculating the AD with 19, is come from the AD plus a BC, but because of B is quite small, we will expect that the BC also, they are not very significant here. We will expect that they come from the AD. Okay, then similar to here, the effect here is very small. So these two is look like it's not very important. So finally, if we choose it here, we will get the factor A, factor B, and factor D, and then we have an AC and the AD. If you base on the 1/2, so what we get if you run the full factorial design? If you run the full factorial design, you will get is a ABD, ACD, AC, and AD. So this one is just now I have. We have here, if we just run the function again, ACD, AC, and AD. So this one will be consistent. But of course, not all the examples will be very easy for you to interpret in this way. Okay, so this one is where you run only 1/2. Then from the 1/2 here, what we will expect from here, we will project it to the full factorial design. Okay, because we are not run the full factorial design, we only run for one half of here. Then from here, we try to guess what are the important factors will be affected your whole analysis. So from here, we make the conclusion on the overall design. Okay. So this one is what is the first example I want to go through with you. Okay. I think